Welcome to the Deep Dive. This week, we're taking a critical look at the most important semiconductor news from June 21st to 28th, 2025. This deep dive is really tailor-made for you, whether you're an investor charting market movements or maybe an industry professional just navigating this incredibly dynamic sector. The sources you've shared, well, they offer an invaluable lens into the sector's health, its primary growth drivers, and the significant challenges that have emerged over just the past week. Our mission today is simple: extract the most significant developments, maybe some surprising facts, and the crucial implications for anyone tracking this market.
What's truly fascinating when you look across all these reports, from global market forecasts to intricate design innovations and even complex global strategic moves, is that AI isn't just some fleeting trend. It is fundamentally reshaping the landscape. It is the core why behind nearly every major headline we've seen this week. It's driving the industry forward in really unprecedented ways.
That's a strong assertion right off the bat. Makes me want to dig in immediately. So let's unpack this with some, well, fascinating projections straight from Semi. We're talking about an explosive surge in advanced chip-making capacity, and it seems directly tied to this AI revolution. What does this immense growth mean for investors and industry players? Looking at the supply chain, the overall market dynamics.
The figures are, frankly, quite striking. Global semiconductor manufacturing capacity is projected to grow at a compound annual growth rate, a KDG, of 7% from 2024 to 2028. That ultimately reaches an incredible 11.1 million wafers per month. So for investors, the immediate insight here is robust, sustained demand. That signals significant opportunities not just for chip makers, but really across the entire equipment and materials supply chain.
Right, the whole ecosystem benefits.
Exactly. But the real headline, though, is the advanced node capacity. We're talking 7 nanometer and below. That is expected to surge by a staggering 69%.
69%, wow.
Yes. It's jumping from 850,000 wafers per month to 1.4 million wafers per month by 2028. And this isn't just general expansion. AI is explicitly named as the primary growth driver. It's boosting demand for high-performance chips across intensive AI training and inference, and also cutting-edge applications like AR/VR and robotics.
That incredible capacity growth, it really underscores the scale of ambition here, but it's not just about producing more chips, right? It's about pushing the absolute limits of what a chip can actually do. Which brings us, I think, to the fascinating race towards sub-2 nanometer nodes. How aggressively is the industry betting on these bleeding-edge nodes, and are those investment figures as bold as they seem, especially in the current economic climate?
Oh, this aggressive push is indeed very significant, and the investment confirms that commitment. Advanced manufacturing nodes of 2 nanometer and below, they're projected to grow from under 200,000 wafers per month in 2025 to over 500,000 wafers per month by 2028. That's a huge jump.
More than double.
Exactly. And we're looking at some key milestones arriving very soon. Think about this. 2 nanometer chips are set for mass production as early as 2026.
2026.
With 1.4 nanometer deployments falling closely in 2028, this signals a really bold acceleration in manufacturing sophistication and clear confidence in future demand. From a financial perspective, capital investment in advanced chip equipment. It's set to rise from US $26 billion in 2024 to over US $50 billion in 2028.
That's a massive 94% increase.
It is, and focusing even more granularly, investment specifically in 2 nanometer and below wafer equipment is projected to double, from US $19 billion in 2024 to US $43 billion in 2028. This level of investment, well, really underscores the industry's belief in the long-term value and necessity of these next-generation capabilities, despite any, economic headwinds.
And we're already seeing this immense investment translate into strong financial performance across the industry, aren't we? What do the latest Foundry revenue reports tell us about who exactly is benefiting from this AI-driven surge? Are we seeing a shift in the traditional pecking order, perhaps? Or are the established players simply solidifying their lead?
We are seeing clear beneficiaries, and yes, it does reinforce the strength of established players. The first quarter global semiconductor foundry revenue rose an impressive 12% year-over-year, reached $72 billion.
$72 billion in Q1 alone.
Yes, and this isn't just general growth. It's really a testament to the surging demand for the foundational components of this AI revolution. William Lee from Counterpoint Analyst provided a very clear insight on this. He stated, and I'm quoting loosely here, AI adoption remains the centerpiece of semiconductor growth, reshaping priorities across the foundry supply chain and reinforcing TSMC and packaging players as central beneficiaries in this new wave.
So TSMC and packaging, that makes sense.
It highlights that the foundational manufacturing capability, particularly TSMC's advanced node leadership, and the crucial role of advanced packaging. That's where much of the immediate financial upside is being realized, directly because of AI's, well, voracious appetite for high-performance silicon.
Okay, so AI is undeniably driving the demand for more powerful chips. We've covered the manufacturing capacity, the investment. But what's equally fascinating, I think, is how AI is now actively driving the creation of those chips. The Design Automation Conference, DAC, recently gave us a really insightful look into this revolutionary shift in the design process itself.
Yes, this is a profound shift. It impacts everything upstream. The central theme at DAC was how AI is, well, permeating the entire semiconductor ecosystem. That was the phrase used. It's fundamentally changing not just the AI chips themselves, but also the very design tools used to create them and the methodologies employed to ensure their reliability.
So it's not just the what, but the how.
Exactly. AI's use in electronic design automation, EDA, is expanding rapidly beyond mere pattern recognition. It's now moving into what they call generative and agentic applications. Think of agentic as the AI not just giving you information, but actively taking steps and solving complex design problems on its own, almost like a proactive design assistant.
Ah, okay, so it's more autonomous.
Precisely. And this is driving major shifts in overall tool workflows. For instance, Siemens unveiled an AI-enhanced toolset for the EDA flow. It allows customers to integrate their own data and create custom workflows using AI across digital implementation, sign-off, custom IC development, the whole gamut.
Right.
And in a concrete example of collaboration, Rapidus and Siemens also plan to develop a reference flow and process design kit based on the Calibre platform specifically for Rapidus's cutting-edge 2-nanometer process.
So tailoring the tools for the newest nodes.
Yes. These agentic AI capabilities are allowing tools to autonomously solve complex design problems, which, dramatically reduces engineer workload and significantly enhances design flexibility. Furthermore, AI co-pilots are accelerating things like register transfer level, or RTL, and test bench creation.
Basically, helping engineers write the chip logic and test it faster.
You got it. Helping engineers write the foundational logic for chips and quickly create test scenarios. And it benefits both novice and expert engineers through assisted and creative modes. The industry is increasingly leveraging large language models, LLMs, and simulation data to enhance abstraction, speed up development, and importantly, bridge skill gaps across diverse design teams.
That makes sense. As chips get exponentially more complex, especially to handle these AI demands, we're also seeing this massive push into new sophisticated architectures, things like 3D ICs and chiplets. This isn't just some technical detail for engineers, is it? It feels fundamental to achieving future performance and unlocking new capabilities. But what new challenges does this present for designers? And importantly, how are those challenges being addressed?
Absolutely fundamental. Multi-die architectures, like 3D ICs, are proving crucial to meeting AI's intense processing demands. Instead of building chips like a flat city sprawling outwards, 3D ICs stack components like a skyscraper.
Good analogy.
It allows for much more processing power in a smaller footprint and effectively overcomes the physical and performance limitations you see in traditional planar systems on chip, or SoCs. To support this, Siemens introduced a suite of tools specifically for planning, implementation, and management of these heterogeneously integrated 2.5D and 3D IC designs, along with thermomechanical analysis software to identify the electrical impact of stress right down at the transistor level.
So managing the heat and the physical stress of stacking.
Critical aspects. Similarly, Arduous introduced new software that specifically enables IP teams to package and prepare hundreds, maybe even thousands, of components for seamless integration into chiplets or SoCators. What we're observing is really a robust growth of the IP ecosystem. Companies are actively expanding their portfolios to include chiplets, all to support this modular design approach in advanced packaging.
The building blocks are becoming more standardized, more plug and play.
In a sense, yes. Even research is progressing rapidly here. Researchers at the Institute of Science Tokyo developed power supply technology for 3D integrated chips employing stacked computing architecture and precision high-speed bonding techniques. However, despite these advancements, critical challenges remain. Thermal dissipation, just dealing with the heat generated by these stacked components and the precise alignment of interconnects, those are still significant hurdles for achieving widespread 3D IC scalability.
Right, the physics doesn't go away. Okay, so beyond the core chip design itself, AI's influence seems to be reaching into every corner of the ecosystem, from real-time system monitoring to advanced data transfer solutions, even entirely new computing paradigms. What are some of the standout innovations that caught your eye this week in these areas, and what's their broader impact?
Well, a few distinct innovations stood out, really showing the pervasive nature of AI's influence. First, the concept of digital twins is gaining significant traction. These are real-time models and monitoring systems. They can model anything from individual chips all the way up to entire data centers.
So a virtual replica running in parallel.
Exactly. Enabling predictive maintenance and crucial efficiency optimization. This is key for managing the intense computational loads of AI. Second, electro-optical integration. It's making major strides. MediaTek, for instance, is partnering with Renovus. They're delivering 8x800G co-packaged optics, or CPO solutions, leveraging MediaTek's Days and Renovus's Odin engine.
Moving light closer to the silicon for faster data transfer.
Precisely. This strategically positions them in hyperscale photonic interconnect ecosystems, which are absolutely crucial for the incredibly high bandwidth data requirements of AI applications in data centers. Third, we're seeing an increasing demand for advanced metrology, the science of measurement. It's vital for quality control in advanced manufacturing. Bruker recently installed its 15th Insight WLI 3D optical metrology system to a leading IC manufacturer. And that's part of a larger order for 27 systems in 2025.
That's a lot of high-end measurement gear.
It reflects the growing need for high-performance metrology to support the stringent advanced packaging requirements in AI chip manufacturing. You can't build what you can't measure accurately. And finally, in emerging computing paradigms, we saw significant funding rounds. Snowcap Compute launched with $23 million in funding for its superconducting computing platform.
Superconducting, so very low temperatures.
Yes, specifically for low-temperature AI, quantum, and high-performance computing, or HPC, systems. Separately, Connect raised $10 million for its room-temperature quantum networking hardware. These are glimpses into future computing architectures, designed to handle problems currently beyond classical silicon.
Fascinating stuff. The competitive landscape, though, it feels incredibly dynamic right now, especially with AI driving so much change. You mentioned MediaTek's collaboration earlier. Their overall evolution, for instance, offers a clear example of how major companies are strategically adapting to this AI imperative. Are they truly carving out a unique niche here? Or are they following a path others have tried? What sets their approach apart?
Well, MediaTek is making a very decisive and, I'd argue, unique pivot. They are evolving from being a traditional system-on-chip and SoC vendor to becoming a full-stack AI ASIC platform provider.
Full stack. So involved at every layer.
It's exactly. From leveraging cutting-edge 3-nanometer and TSMC N2 nodes, the most advanced manufacturing tech available, to integrating advanced SerDes at incredibly high speeds like 128G and 224G, and utilizing co-packaged optics and co-packaged computing, CPO-CPC, packaging for optimized power, performance, and area, PPA.
PPA always critical.
Absolutely, because it dictates how efficient and powerful a chip can be. A significant aspect of this transformation is that collaboration with NVIDIA we touched on. They've co-developed the GB10 AI module and NVLink fusion architecture. Together, that enables over 1,000 TOPS trillions of operations per second of compute and modular connectivity, critical for large language model training and smart edge applications.
So big compute power, but also connectivity.
Right. And for edge intelligence, they're deploying next-gen 3-nanometer sockets featuring over 50 TOPS NPU for multimodal AI inference across smart devices, targeting low-latency, low-power on-device agents. And in the automotive sector, MediaTek launched DX1, which is the first 3-nanometer cockpit chip integrating an NPU and an RTX class GPU.
Aiming straight for premium vehicles.
Precisely. It's aimed at capturing premium smart vehicle segments, and it's designed with NVIDIA Drive compatibility, positioning them firmly in a high-value, high-growth area. So this isn't just following, it really feels like leading with a comprehensive, integrated approach.
Okay, that makes sense. Beyond these individual company plays like MediaTek's, we're seeing governments and major players making strategic moves, shoring up their supply chains, fostering innovation regionally. What's the global picture telling us this week about these larger, often geostrategically motivated shifts?
Globally, the emphasis is clearly on supply chain resilience and regional self-sufficiency. It's a direct response to geopolitical tensions and the increasing strategic importance of semiconductors. Continental, for instance, established a Fabless Advanced Electronics and Semiconductor Solutions, or AESS, organization. It's specifically to design and verify automotive chips, with global foundries acting as their manufacturing partner. This move is explicitly aimed at reducing geopolitical risks within their supply chain for a critical sector.
De-risking their auto chip supply.
Exactly. Conversely, Intel announced the shutdown of its automotive business unit, leading to layoffs for the majority of employees from that division. Seems like a strategic reallocation of resources towards core competencies.
Interesting contrast there.
And separately, Wolfspeed announced a restructuring agreement with creditors. An official Chapter 11 bankruptcy filing is expected by July 1st, though operations are anticipated to be fully funded through post-restructure cash flow. So, navigating financial challenges. Now, looking at specific regions, we see a really diverse patchwork of strategic responses and advancements. In Asia, Huawei's new MateBook laptop, based on 7-nanometer technology, well, it's seen by many as a clear sign that U.S. export restrictions, while impactful, may not be entirely halting China's advancement to the leading edge of semiconductor manufacturing. Highlights their resilience.
Still pushing forward despite restrictions.
Seems so. Also notable from China, May exports to the U.S. decreased dramatically. We're talking 80% for rare earths and 93% for rare earth magnets compared to the prior year. This signifies a potential shift in global resource dynamics, maybe a reduction in a critical supply chain link.
That's a huge drop.
It is.
Yeah.
Meanwhile, SK Hynix plans to build a new packaging and test facility in Cheongju, South Korea, underscoring the critical importance of advanced packaging capabilities for next-gen chips, especially for AI.
Packaging continues to be key everywhere.
Absolutely. Over in the Americas, beyond specific company news, Canada's Fabric project awarded CAD $13.4 million, about US $9.8 million, to 20 projects, focused on advanced sensors and other semiconductor products. That represents a significant investment in fostering domestic innovation there.
Canada's stepping up its game.
And Xanadu also opened an advanced photonic packaging facility in Toronto, Canada, specifically targeting ultra-low loss coupling for photonic ICs, a key area for high-speed data transfer. And Skywater Technology expects to close its acquisition of Fab 25 on June 30th, expanding domestic U.S. manufacturing capabilities.
Okay, what about Europe?
Across Europe, the U.K. published its 10-year Modern Industrial Strategy Plan. It includes a clear focus on semiconductors and quantum technology, signaling a long-term commitment to these strategic sectors. Complementing this, their new Global Talent Task Force will spend £54 million to attract researchers, directly addressing that critical talent gap we keep hearing about.
Money targeting talent attraction.
Yes. And Bosch will invest more than $2.5 billion to advance AI innovation by the end of 2027. That's a major private sector commitment in Europe. Fraunhofer's European Test Reliability Center, ETRC, opened in Chemnitz, Germany, is focusing on development, testing, validation of wide bandgap ICs, chiplets, MEMS, photonics, crucial infrastructure for advancing robust European chip development. And in Scotland, Neuronix will build a new nanofabrication center for magnetic sensors in Glasgow as part of a larger investment zone, showcasing localized strategic investment.
Lots of activity globally. But this explosive growth and technological advancement, well, it doesn't come without its own set of significant hurdles. Perhaps the most pressing for the long-term health and sustainability of the industry, especially for investors looking at sustained growth, is the looming talent crisis. How are these challenges really manifesting, and what initiatives are underway to address them?
The industry is indeed facing a profound semiconductor talent crisis. The data suggests a need to add, well, a staggering 1 million skilled workers by 2030 just to meet projected growth.
1 million workers, that's huge.
It is. And it's compounded by a high turnover rate and a notable shortage of leaders within the industry. Furthermore, declining enrollment in electrical and computer engineering, ECE, programs in universities is a significant concern for the talent pipeline. It threatens future innovation.
Fewer engineers coming through the system.
Right. And the rapid integration of AI is also fundamentally reshaping the required skill sets. AI and machine learning have actually surpassed systems architecture as Europe's most desired skill. There's a growing need for software engineers specializing in embedded programmers, even over traditional design engineers. This shift means the industry needs to retrain its existing workforce and attract new talent with different specializations.
So what's being done about it?
Several initiatives are underway. NatCast, for instance, launched the NSTC Top Workforce Solutions Recognition Program in the U.S. It focuses on technician certification programs in community colleges, addressing the urgent need for skilled technicians on the factory floor. In South Korea, Amkor Technology Korea is partnering with Cheonam National University for hands-on training and R&D in semiconductor packaging and testing. Canada's Semiconductor Council reported that while 70% of Canadian companies plan to at least double in size, their growth is critically dependent on access to skilled talent, highlighting its universal challenge.
Growth bottlenecked by talent.
That's the fear. And in an interesting development, Central New Mexico Community College, collaborating with Sandia National Laboratories, will offer a 10-week quantum technician boot camp, looking to build talent for future computing paradigms.
Addressing current and future needs.
Okay.
Another major challenge, particularly for investors looking at long-term infrastructure and, frankly, environmental impact, is the staggering energy demand being projected for AI. These numbers are truly eye-opening. They could significantly impact the scalability and sustainability of all these AI initiatives.
They absolutely are eye-opening, and the implications are vast, both for energy grids and environmental planning. The U.S. Energy Information Administration reports that electricity used for commercial computing could actually surpass space cooling and ventilation by 2050.
Wow. More power for compute than for cooling the buildings.
That's the projection. It means the actual processing power itself, driven heavily by AI, will be the dominant energy consumer in these facilities. Even more immediately, Deloitte estimates that by 2035, power demand from AI data centers in the U.S. could grow more than 30 times.
30 times.
Yes, reaching an astonishing 123 gigawatts, up from just 4 gigawatts in 2024. This level of power consumption presents a monumental challenge for energy infrastructure development, grid stability, overall sustainability goals. It's a critical consideration for any long-term investment in this sector.
A huge factor. Now, as chips become more intricate and interconnected, especially with the rise of multi-die architectures, ensuring their reliability and security becomes absolutely paramount. What are the latest developments on this front, both in terms of preventing failures and combating, well, the ever-evolving cyber threats in this complex ecosystem?
Reliability is indeed critical, especially with stacked and modular designs. For complex chiplet-based systems, continuous monitoring is essential to prevent things like silent data corruption and aging, which can degrade performance or lead to catastrophic failures over time.
Catching problems before they escalate.
Exactly.
Yep.
On the cybersecurity front, there's really a multi-pronged effort. CISA and the NSA have published a joint guide identifying obstacles and solutions for adopting memory-safe languages in software development, pushing for more secure coding practices from the ground up to prevent common vulnerabilities. The EU member states have also issued a roadmap for using post-quantum cryptography in cybersecurity, preparing for a future where quantum computers could potentially break current encryption standards. That's a proactive measure for long-term security.
Getting ahead of the quantum threat.
Trying to. Interestingly, AI is also being leveraged in security itself. Caspia Technologies will integrate its generative AI security platform with Siemens Questa 1 smart verification software to expand security verification capabilities, effectively using AI to help secure AI chips.
AI policing AI.
In a way, research is ongoing into areas like hardware Trojans detection using graph neural networks in RTL designs, basically looking for malicious circuits embedded at the chip's core. Other research includes unified memory protection and even agentic large language model approaches for system-on-chip security verification, like SVLLM from the University of Florida. Furthermore, industry conferences like VulnCon 2025 focused on hard problems in common weakness enumeration, or CWE, and how to leverage CVE root cause mapping to prevent new vulnerabilities. And CISA has continued to issue new alerts and advisories, underscoring the constant and evolving threat landscape the industry must contend with.
It's a constant battle. Okay, beyond the broad trends and the major challenges, we also have some very specific market developments and some exciting cutting-edge research coming out this week. What caught your eye as particularly noteworthy in these niche or emerging areas? Things that might hint at future shifts or opportunities.
Yeah, a few distinct points emerge. In the automotive sector, the global automotive LiDAR market, crucial for autonomous vehicles, is projected to quadruple by 2030. But interestingly, Chinese LiDAR suppliers are expected to account for a dominant 89% of the total market.
89%, that's huge concentration.
It indicates a significant regional concentration of supply and a potential future power shift in this key component area. In quantum computing, we're seeing continued investment interest. New funding rounds for superconducting computing platforms like Snowcap Compute and quantum networking hardware from Quinect. These are significant for pushing the boundaries of computing. Research is also advancing rapidly, particularly in high-precision, low-cost fabrication of semiconductor qubits, making quantum potentially more viable down the road.
Making quantum manufacturing easier.
That's the goal. Looking broadly at R&D, McKinsey anticipates that AI could boost research and development throughput for semiconductors by almost 60%, with design generation seeing the biggest impact.
60% boost in R&D speed.
That's the projection, a massive productivity leap for the entire industry, if it pans out. For the silicon wafer market, which is foundational to all chip production, 2025 revenues are expected to rise about 3.8% to $14 billion. And TechSet predicts a solid 6.4% annual growth through 2029. Consistent growth signals healthy, underlying demand for the most basic building block.
Steady growth at the base.
Right. And in terms of specific product news, XCIP expanded its 180 nanometer process with a new isolation class for enhanced single-photon avalanche diode, or SPA integration, critical for LiDAR and 3D imaging apps. Faraday Technology also made its 10G SerDes IP available on UMC's 22 nanometer process, supporting high-speed data transfer within chips, essential for today's data-intensive workloads.
Okay, so bringing it all together, what does this all mean for you, the listener? Whether you're an investor charting these market movements or perhaps a professional navigating this industry day to day, it's clear we're in an unprecedented phase of transformation. AI isn't just a technology being put into chips anymore, it's the fundamental driving force behind profound changes in manufacturing capacity, investment strategies, the very design processes themselves, and even the industry's workforce and security needs. The underlying message seems to be one of aggressive growth and rapid innovation, but also, well, significant complex challenges that need addressing.
Absolutely. And if we connect this to the bigger picture, it really raises an important question, doesn't it? As the semiconductor industry sprints, and it really is sprinting, to meet the relentless demands of AI, and as AI tools become ever more central to the design and manufacturing process, are we adequately preparing our human talent and our energy infrastructure for this exponential curve? And what are the long-term implications for global competitiveness, especially as regions make increasingly strategic plays to secure their own supply chains and foster domestic talent?
A fantastic thought to mull over, and certainly a crucial one for anyone invested in this space, professionally or financially. Thank you for diving deep with us this week. Until next time, keep exploring those insights.